Starting today, we will be introducing the subject of a different types of conversion of solar energy, namely photovoltaic energy conversion. Now, essentially in photovoltaic energy conversion, you seek to convert the solar energy directly into electricity without going through the intermediate stage of converting first into thermal energy and then electrical energy. So, it is a direct conversion of energy from sun's rays into electrical energy. In essence, it works on the principle of a simple p-n junction, about which I suppose you have all learned. So, I will not go into the essential details of that, because I will be assuming that you and any engineering student who attend this course would be knowing. So, what is the essential point? In any semiconductor material, say silicon, if you dope it with certain things, then the balance of electrons and holes changes. If you dope it as p type, then you have excess of holes. If you dope it with n type, you have excess of electrons. And what is the thing you dope with for p type? For p type, phosphorus in general, yes. And for n type, no, that is another semiconductor. You forgotten? Does not matter. Initially, let us start with just assuming that we have got a p type semiconductor and a n type semiconductor, and those details of how to dope stuff like that will come later. Now, if you have a p type semiconducting material or n type semiconducting material, as you know that in a semiconductor we can identify a band gap between the conduction band and the valence band. So, normally this would be depicted as one band for the conduction, another band for the valence, and the band gap for the case of silicon is about 1.107 electron volts. For silicon, it would be 1.107 eV. So, this band gap. Electrons, when they are in the conduction band, they are conducting. Holes, when they are in the valence band, they are conducting, and the average energy of the electrons would be given by a level called the Fermi level. So, the Fermi level would be a level in between these two, and in case of the p type semiconductor, the Fermi level will be closer to the valence band. In case of the n type semiconductor, it will be closer to the conduction band, right. That was the basic the semiconductor theory that you all learned. Okay. So, there would be a level, say in case of a n type semiconductor somewhere here, that will represent the Fermi level. So, this is the conduction band, and this is the valence band, and this is the Fermi level. Representing the average energy of the electron in that material. Now, when you join a p type material and a n type material to produce a p n junction, what happens? That also you have learned. The Fermi levels become equal, and as a result the band bends like so. The Fermi level becomes equal, and if in this side it is a p, then the valence band is somewhere here and the conduction band is somewhere here, and in this side if it is n, then the conduction band is somewhere here and the valence band is somewhere here, and so there is a band bending, right. So, this is the basic theory of p-n junction you have learned. Because of the band bending, the electrons find it difficult to go up the hill, holes find it difficult to go down the hill, and therefore, electrons flow this way and the holes flow this way is effectively blocked, and therefore, it acts as a diode, right. So, that is the basic theory that you have already learned. In case of the photovoltaic cell, we essentially use of this property, but in addition to that, what is not there in the normal diode is that light is falling to a place where very close to this band bending region. As a result, as the light is incident upon the material, the electrons will absorb the photons, and if the photon energy is bigger than the band gap energy, then a electron hole pair is created. Electrons are knocked off from their positions to make them free. As a result, you have a electron going to the conduction band and a hole. Naturally, when electron is knocked off, there is it leaves behind a hole. So, hole goes to the valence band. So, in other words, it results in the creation of a electron hole pair. Now, imagine what will happen if an electron hole pair is created somewhere here. So, electron hole pairs are created, and imagine that one electron hole pair is created somewhere here. Do you understand why the electron hole pair was created? Essentially, if the light has an energy bigger than the band gap energy, then it knocks an electron off its site in a particular atom, makes it freely movable in the bulk material. As a result, the electron goes to the conduction band, leaves behind a hole which is also free to move, that is in the valence band. So, suppose it has been created here. Now, electrons have the natural tendency of flowing downhill. So, it will naturally go like this. Supposing more electrons are created somewhere here and holes have been created somewhere here. Then the electrons from this side will flow down the hill, and holes tend to bubble up. They behave like bubbles in water, that means they tend to flow up. So, the holes will flow like so. As a result, there will be a larger concentration of holes in this side and a larger concentration of electrons in this side, thereby producing a voltage difference. Okay. And if you put some kind of a charge collector in the two sides and connect by means of a resistance, then the charge flows continuously and you have the flow of a current. Okay. What will be the current direction? No, outside. It should be like this. Huh? So, this is the essential theory behind the photovoltaic cell. So, unlike the normal p-n junction diode that you have come across, what additionally is here? The creation of the electron hole pair, and the electron hole pair has to be created close to the band bending region. which means that a large number or large amount of area has to be exposed to the sunlight and the whole p-n junction has to be over that area. Okay. Which means imagine that you have got the thing like this, a on which the light falls, the whole thing has to be the p-n junction, the whole thing. So, you might imagine that here I will just blow up by means of a larger thing, the p n junction might be somewhere here. That means, the p n junction has to be over the whole surface, which is the extended surface. So, how to make such a thing? I will come to the production process per se a little later, but essential structure is that below it there has to be some kind of a metal substrate in the sense that you have to collect the charge. So, there has to be metal contact, and that metal contact is in the form of, if I draw the side view, it will be something like this. First there is a metal substrate, then you have a reasonably large layer of P, then you have a smaller layer of N, and here is your p-n junction. So, light falls on the top surface and the depth of the n layer is made such that the light penetrates up to the junction level. So, it is actually very thin layer, it is not a thick layer. It is not that you take some n and you take another take some p, take another n and just put it like this. No, it is not like that. It is grown in a different way. I will come to that later. So, here is the metal substrate, here is the P layer and here is the N layer. Okay. And this fellow is the P N junction. But there has to be some way of collecting the charge there. At the bottom side, collecting the charge is no problem because you already have a metal contact, but at the top you only have a p type semiconductor level. There has to be some way of collecting the charge. So, the way to collect the charge is to lay a grid of metal. The more extensive the grid, the more will be the blocking of the sunlight, remember. So, you have to allow certain maximum amount of sunlight to pass through. So, it is not really covering the whole surface, rather it is like a metal a collection of metal fingers that are laid on the surface, which collect the charge from the top level, and then it is connected to with by means of some kind of a load through the bottom level. Okay. So, that is the structure of the p-n junction, structure of the photovoltaic cell. The manufacturing process and other things I will come to a little later. Now, what are these made of? In general, these are made of silicon. In general, as yet whatever photovoltaic cells you see in India, they are all made of silicon. But then there are a few things that you need to understand carefully. First thing is that the p-n junction being here, the electron hole pairs are created all right, and they go to different directions all right, but before they are collected by the contacts, they may also recombine. Okay. Normally they may also recombine. As a result, the current generation will be less, current generation will be less. So, in order to avoid that, we need to ensure that there is minimum recombination. Now, it so happens that if there is any deformity in the lattice structure, these act as recombination centers. For example, if it is a single crystal, that means all the silicons are arranged in a nice array, then obviously there is no deformity and nothing acts as a recombination center. But if there is a crystal here, another crystal there, in between there is a crystal contact, then there are dangling bonds, bonds that are unsatisfied, and these dangling or unsatisfied bonds act as a recombination center. So, it follows immediately that it is desirable to have a single crystal of silicon to make the photovoltaic cell. In fact, almost all the photovoltaic cells that are commercially manufactured in India are single crystalline solar cells. But also it is a fact that there is a great expenditure in making the single crystal, and therefore, some companies prefer to make it cheaper by sacrificing some amount of efficiency. In that case, they use what are known as the polycrystalline silicon solar cells. So, we can now enumerate a few possibilities. Number 1, the single crystal polycrystalline and polycrystalline means there is a crystal structure, but the whole thing is not made of one single crystal. So, that is the polycrystalline solar cells. For example, in India the Tata BP Solar, that company manufactures the polycrystalline solar cells, while BHEL, CEL and companies like that produce single crystalline solar cells. There is another type of solar cell where in order to make it cheap, very cheap, you do not make a crystalline structure at all. These are called the amorphous silicon solar cells. Obviously, their efficiency is very low, but the cost of production is also very low. For example, in calculators you will find a small, some calculators have small solar cells, right. These are all amorphous silicon solar cells, because there the amount of power necessary is very small. So, they simply put some amorphous silicon solar cells. So, there are 3 types. Amorphous silicon solar cells are rarely considered for bulk power generation. They are considered for that kind of specialized power generation where the power requirement is small, but at the same time you have to remember that amorphous silicon solar cells are very cheap to manufacture, and moreover there it is possible to make thin films. So, a thin film laid on something can also work as solar cell. So, that can be possible with amorphous silicon, which is not possible with single crystal, because there is hard single crystal. Now, you might ask that while talking about conversion of one form of energy to another, we had talked about the quality of energy, right, in the beginning of the course, quality of energy. Electricity is obviously high quality energy. What is solar energy? Is it high quality or low quality? Low quality. So, by the law of thermodynamics, there has to be some kind of a limit. There must be some kind of a limit. So, it is not possible to have 100% conversion of solar energy to electrical energy. What could be the sources of the inefficiencies? One, what? Combination? Recombination is one. That means, after the electrons and holes separate, they recombine. That recombination is one source of, but before that let us start from the start. What about the electron hole pair generation itself? when it comes to generation, will it be 100% efficient? No, not because see in the solar spectrum there would be some wavelengths that contain energies that are lesser than the band gap energy. If it is lesser, they will not be able to knock off the electrons of their site, and therefore, they will not be able to create an electron hole pair. There will be some frequencies that are above, that contain energy above the band gap energy. So, if something has energy that is say 1.5 times the band gap energy, only the band gap energy is necessary in order to create the electron hole pair. Where does the rest of the energy go? Not kinetic energy, no, not kinetic energy. They simply are wasted as heat. Kinetic energy, the question is there for photoelectric effect. The photoelectric effect is where you have got a metal surface, light shines and electrons are knocked off the surface, they go into the surrounding air. This is not what we are considering here. We are considering the situation where the electrons stay in the bulk material, only they are knocked off their site, so that they become free to move in the material. So, naturally the energy that these electrons absorb in order to go from the in order for the creation of the electron hole pair is exactly equal to the band gap energy. That is what is needed. The excess energy goes as heat. So, if the light has an energy the specific photons have energy less than the band gap energy, then that is also wasted as heat. If that is above, that is also wasted as heat. Okay. That is why it is necessary to choose a material that has the proper band gap for the solar light, and silicon is reasonably good. There are other materials that are being considered now, for example, germanium, for example, other materials like cadmium sulphide, copper sulphide, that kind of material. But nevertheless, at the introductory level, you should know that most of the solar cells that are produced are made of silicon, which have band gap of about 1.107 electron volts. So, we now understand in what way the laws of thermodynamics works. Now, in the solar cell, then we have to come to the idea of how to make the single crystal solar cell, because that is the most predominant. Single crystal solar cells obviously have the largest efficiency. Normally, the efficiency would be of the order of say 20 to 25%. There have been good well manufactured solar cells reported with efficiencies of the order of 27 to 28%, but the run of the mill standard industrially produced solar cells would have efficiency between 20 to 25%. If it comes below that, then you would know that cell is bad, that is it. Now, the efficiency of the polycrystalline solar cell would be of the order of 10% to 15%, and the efficiency of the amorphous silicon solar cells would be of the order of 3% to 5%. Okay. So, this is very less efficient, this is medium, and this is reasonably high efficiency. So, you would say here the efficiency is somewhere between 20 to 27%, and here the efficiency is say 10 to 15%, and here the efficiency is 3 to 5%. So, naturally we need to understand how to make these, and that should tell you how the solar cells are actually manufactured. Now, in solar cell manufacture, the essential raw material is what is known as solar grade silicon. The solar grade silicon means that from the SiO2 or quartz steel, quartz sand, by means of a reduction process, first silicon is produced. Now, that silicon contains many impurities, and for various different purposes you need to remove the impurities to different extents. Highly refined silicon would be needed for the highly refined kind of activity like production of VLSI chips and stuff like that. Obviously, for solar cell production you do not need that kind of refinement, you do not need that kind of refinement. So, what is normally done is some amount of impurities can be allowed, thereby reducing the production cost. Ultimately, when the basic material is produced, then you have to make somehow a single crystal. This is done by first taking a crucible, heating it up so that it melts. So, there is a molten material and you have to add a seed in order to start the formation of a crystal. So, there is a metal contact at the bottom of it, there is a silicon seed which is just touching the surface of the silicon, molten silicon, right. Now, it is cooled very slowly, so that only the surface, close to the surface, it becomes slightly lesser than the melting temperature, so that the silicon starts to solidify. As it solidifies and gets in touch with that seed, it settles there, and as a result the crystal starts to grow. As it starts to grow, this metal holder is pulled up slowly, okay, very slowly. As it is pulled up, at the contact more and more metal will be formed, more and more silicon crystal will be formed, and you ultimately pull it up, and what do you produce? A cylinder of silicon, right. So, that is why the silicon, these things are called ingots. The silicon ingots are produced, which are always of a circular cross section. Due to very natural reasons, you cannot really make square or something like that, because you are naturally pulling it up and it is taking the shape on its own accord, and it will automatically take the shape of a circle. So, you pull up a cylinder. Now, this cylinder, up to this, as yet India does not have a facility of making it, though we are now installing such facilities, but as yet these ingots are imported. Then what is done? Then these ingots, that means you have got a silicon structure, these are cut. So, first there is a machining process by which these will be cut into slices. So, you get very thin, about 1 millimeter thick slices, each of which will produce a solar cell. So, that is why the solar cells are circular in shape, circular in cross section. After these are put, the bottom metal contact is first laid. So, 1 meter thick, about this much circular cross section slice is taken, and the bottom contact is first put. The bottom contact is often made by means of first making a paste of powdered metal and then painting the bottom that way, okay, simply, and then when it dries off, you have got a metal contact. Now, you have got the material. Oh, by the way, the material that is produced is essentially p type material. That means, when the ingot is produced, it is already p type. It is not just a raw silicon, already it is doped. So, you have got a p type material. Now, you have got the bottom contact, you have got the p metal. Now, this is taken inside a chamber in which phosphorus vapor is put in. This is heated to a particular temperature, so that the phosphorus vapor goes into the material, thereby creating a layer of N. Okay. And the time of exposure, the amount of vapor that you put in, that decides to what depth it will go. That is why this has to be very precisely controlled, because this, if the p-n junction is found much below at a greater depth, then the light will not penetrate up to that point. naturally the electron hole pair will be created somewhere here, not here. If that happens, then obviously the flow of electron, the electron hole separation will not take place. So, in order for the electron hole separation to take place efficiently, the electron hole pair has to be created very close to the junction. For any material, you know the penetration depth. So, you have to exactly make the arrangement in that chamber, so that the p-n junction is produced only to that depth. So, that way you produce a layer of n. Now, the top layer is left. Top layer means the metal fingers. Have you ever seen the screen printing process? Screen printing, by which your marriage cards are printed. If you feel the marriage cards, you will find that it is a bit elevated, you can feel with your hand. Do you know how it is done? You will need to wait till you get married to know how it is done, right? Okay. It is done by the very simple means of a silk screen. There is a frame in which there is a silk screen. Now, people make masks. You can also make masks simply by using some kind of a glue and painting over. The part which is masked will not allow the color or the paint to go in, the part that are not masked will allow the paint to go in. So, some parts of it are masked. You might also mask simply with the help of a bit of sellotape. So, certain places are masked, and then they take the paint on a roller. Okay. They simply take the paint on a roller and press it. As a result, the paint goes through the silk and attaches to the paper that is placed below. Okay. So, they place the paper, the silk screen, and then take the paint with a roller and then paste it. That is how the impression is made. Nowadays, you have got very refined process of making the mask, so that you type something in a computer and that automatically produces a mask, so that you do not have to really do it by means of sellotape or by hand painting the mask. There are ways of doing it automatically, but nevertheless the essential process is that you have the mask. The mask does not allow the paint to go in. The place where it is not masked, that is the place where the paint goes in, and finally that is what you see on the paper. That is how it is made, and that is how, since the paint is a bulk paint, you have a slight bit of elevation there. You can feel with your finger that there is a material there. The top contact of a silicon solar cell is put by exactly the same method, silk screen printing, where again the metal is powdered, very thin powder, and made into a paste. You make a similar kind of mask on a silk screen, and then that powdered metal paste is painted onto that, as a result of which it goes in and sticks to the upper N layer where it is not masked, and that is how the metal fingers are put. Clear? So, metal fingers are put and then that is removed, let dry, and finally, you have the whole thing ready. All these individual ones are connected in series in order to produce a whole panel. Each individual cell will be producing a voltage of the order of 0.8 volts, which is not sufficient for any practical purpose. So, many of them are put in series to produce a voltage something like say 30 volts, which is a useful voltage, and that is how the solar panels are made. Okay. Now, let us come to another issue. The kind of supplies that you have learnt of, for example, the supply in the socket, what kind of source is it? It is a voltage source, right. So, what is the character of the voltage source? It is that the voltage remains constant irrespective of the amount of current you draw. The current you draw depends on the load. Okay. The load that you connect, whether you connect a heater or a bulb or a fan, depending on the current changes, but the voltage remains constant, that is why it is a voltage source. Okay. Now, notice what is happening here. You have got the solar light coming in and the separation of the charges. Separation of charges means what? Charges flowing in the opposite direction means what? It is not voltage, it is current. So, the incident solar radiation produces a current. So, it becomes effectively a current source, not a voltage source. It becomes effectively a current source, not a voltage source. So, effectively you have, depending on the amount of solar radiation received, a current source. So, if you want to produce some kind of a equivalent circuit, you would say that I have got a current source. The current source's quantity, the current is actually dependent on the amount of solar radiation received. So, this is called the photocurrent or photocurrent, IPH. So, one thing to remember, very important, most people do not understand it properly, that is there is a fundamental distinction between the photovoltaic source and any other normal type of source that you come across in everyday life. The ones that you come across in everyday life are voltage sources, while the photovoltaic source is a current source. Okay. Now, what happens? You have got after all the p-n junction, and the p-n junction implies that it is a diode. So, what will happen if say you do not connect anything? If you do not connect anything, then there will be a voltage difference, and the voltage difference will produce a current through the diode. A forward bias current is through the diode. See, it is a p-n junction where this is positive, this is negative, it is forward biased. So, forward bias current through the diode, as a result of which, if you connect nothing at the output side, there will be the current generation and the current will be shorted through the diode. Okay. So, this will be like so. Okay. Because this is a p-n junction, this is a diode. Here is a generation of light which will be shorted through the diode, if there is no connection to the external world. Now, if there is a connection to the external world, what happens? There is a current flow, all right, as a result of which the open circuit voltage that was there, which was if it is not connected, then there will be some voltage which allows the full current to be shorted through. But if there is an external voltage, then this voltage will reduce, but nevertheless there will be a voltage due to which there will be a current. So, this diode will remain, but then you have to connect some external stuff here. So, suppose I connect some external stuff, I will do it with a different color with a purpose. The moment you do this, there will be a current flow, some voltage will appear here, this voltage will be seen by the diode, and the current through the diode will be that due to that voltage. And you know how much is the current through the diode? The diode current I d is I naught e to the power the diode voltage. So, okay, the diode voltage divided by a factor. Yes. So, no. Here it is, the electrons charge q, right, -1. Huh? So, this contains all the constants and this is the voltage the variable quantity which is the voltage here. So, this current will still keep on flowing and the rest of the current will go through the load, right. The rest of the current will go through the load. Now, it is not difficult to see that there would be a resistance encountered in the passage of these electrons through the bulk material and the passage of the holes through the bulk material. So, the current passage here will encounter resistance as it goes from here to here. That resistance will have to be taken into account. Where does it appear? It appears in series with the load. So, that will be represented by means of a series resistance here. So, that will be called the series resistance R S. So, what is the series resistance? That is the resistance of the bulk material. Not only that, that is the resistance between the bulk material to the metal contacts. They will also be taken into account. They will also come into picture in the R S. So, R S is a combination of all the resistances that the electrons flow through that solar cell encounters. In addition to that, there will be a, you have also have to consider the phenomenon of recombination. That means, the electron hole pairs get separated all right, but before they are ultimately separated and flows to the external load, they recombine inside. Now, that recombination somehow has to be taken into account, because the photocurrent that was produced accounted for the whole amount of electron hole pair generation. But out of that, if a part recombines before going to the load, then that has to be taken into account inside the model of the photovoltaic cell. Okay. So, where will that be? It will definitely not be in the change in the IPH, because IPH is related to exactly related to the amount of photons that are received, amount of solar radiation that is received. Now, if the there is more recombination, obviously it is not fault of the solar radiation. So, that will not be reflected here. It produces the same amount of electron hole pair generation depending on the energy content of the solar radiation. Will it be reflected here? No, because it is a character of the diode. So, it will not be reflected here, but after that a part of it, part of the current that goes here does not go to the load, it is somehow shorted through, shunted. So, naturally the way it has to be represented is by means of a shunt resistance here, RSH. So, what does RSH actually represent? It represents the recombination of the electron hole pairs before it reaches the load. So, here you have the simple equivalent circuit model of the photovoltaic cell. Okay. And this is the load. Now, let us see, can we now produce a relationship between the voltage and the current that are seen by the load? Obviously, we can. Now, let us see, have you drawn this? From this, because I will not be able to display this and the next page together, you look at the circuit diagram, and from there see, first let us consider that the RSH is not there. First, let us ignore, for the sake of simplicity, we will put that in later. For the sake of simplicity, let us ignore the RSH first. So, it is only this part. Then you have the equation as IPH minus ID is equal to I L, I P H minus I D equal to I L load current, all right, fine, which means I P H minus I naught e to the power q v d by gamma k t minus 1 is equal to I L. This has already produced a relationship between this and that. So, let us see. Now, the V D is V L, that is the terminal voltage, load voltage, plus, yes. So, here we need to substitute I P H minus I naught e to the power, now wait, q, here we will substitute, what will it be? V L plus I R L I R S I L by gamma k t minus 1 is equal to I L, all right. By the way, I did not talk about the components here. Here Q is the electron's charge, D is the diode voltage, gamma is a constant, sort of a curve fitting constant. For different diodes, it will have different values varying between 1 and 3 generally. K is Boltzmann constant, T is absolute temperature, right. So, remember that sometimes in calculation you substitute this for centigrade temperature, it is not, it is a absolute temperature. So, you have this equation, you can see that this already has V L and I L, and therefore, this gives the relationship between the voltage and the current as seen by the load, but this is a hopelessly intertwined thing, right. Will you be able to plot the curve? If so, how will you do that? By MATLAB. You have to tell MATLAB how to solve it, because you see a curve means y is equal to f x, right hand side should not have y, right. Here you see they are mixed up. Yeah, you need to solve it by Newton-Raphson method. So, for every value of v you solve by Newton-Raphson method for the value of I L, and then you have to plot the graph. Got it? How to do it? Now, let us, after you have done this, let us make it more can we get V L out of it? Can we get V L out of it? Can we just manipulate this to get V L? I think that will be doable. I think that will be doable. So, you have I L minus I P H or I should say I P H minus I L, that is better, minus I L divided by I naught plus 1 ln is equal to this fellow, right. Now, naturally it is possible to extract V L. So, put this thing down, now we can write it. How do you do it? Q V, okay, so let me write it this way, V L plus R S I L is equal to gamma k T by Q ln I P H minus I L by I naught plus 1. Okay. So, V L equal to this minus I L R S. Fine. So, we have been able to extract the VL in terms of IL. This has been possible only because we have ignored the shunt resistance. Once you ignore, once you take into account, you will not be able to do that, but nevertheless that is how we get some bit of idea about it. Now, you notice that if we keep it open circuited, IL is 0. If IL is 0 and this IL is 0, then you have an expression for VOC open circuit as gamma k T by Q ln I P H by I naught plus 1. ठीक है? Okay. These fellows are all constants. I naught is a constant. I P H is variable dependent on solar energy, and solar energy really changes all over the day. There may be cloudy sky, there may be open sky, there may be slanted radiation coming. So, I P is variable, but you would notice that the open circuit voltage is logarithmically dependent on the IPH ln. As a result, even though the photocurrent may become half because there came a cloud, the open circuit voltage will not reduce as much. Okay. That immediately gives that conclusion that the open circuit voltage will not reduce as much. Okay. Now, I leave it to you. You write similar expressions like this using the shunt resistance. Then you can solve it by Newton-Raphson, plot the graph. Only thing is that you will know these values, Q you know, gamma take a value between 1 and 3, even 1 no problem, K you know, Boltzmann constant, T a normal temperature, these are known things. All right. What would be the order of magnitude of I naught? 10 to the minus 5, 10 to the minus 5 kind of order, right? I naught, what kind of order of magnitude have you seen? 10 to the minus 5. Oh, okay, okay, you can take values like that, though in case of photovoltaic cells, because of the structure is different, it has a bit of different values, but if you are used to that kind of values, take no problem, because you have done problems using PN junctions. So, whatever values you take, but in case of the photovoltaic panel, it will be slightly more than that anyway. So, you can solve and you can obtain the characteristic graph, plot it with V in the x axis and I in the y axis. Okay. On that basis, we will talk in the next class. Thank you. Instrument to measure the incident solar radiation. As you can see, there is a place through which the solar radiation comes, something that you can possibly shade, and if you shade, then you can get only the diffused solar radiation. If you do not shade, you get the direct solar radiation, and the voltage produced is sensed by a standard voltage meter, voltmeter. In this case, we are doing it with a digital multimeter, and the voltage and its proportionality to the actual incident solar radiation is given in form of a calibration chart. So, we read out the voltage, and from there we can find out the actual incident solar radiation by referring to the chart. So when we try to find out the efficiency of any solar collector, the incident energy has to be found out through the pyranometer reading, and the energy that is gained is to be found out from the temperature difference between the inlet side and the outlet side, and the flow rate. The flow rate can be measured either by a flow meter or simply by collecting the water in some kind of container over a given period of time and then measuring it with a simple measuring cylinder.